Well, welcome everyone, and thank you for joining today's webinar. We're going to explore how organizations can unlock operational intelligence using real-time digital twin powered by graph databases. So we'll cover what a digital twin is, why graph technology is uniquely suited to enable them, and then we'll walk through several real-world examples showing how enterprises are using these capabilities today to drive efficiency, resilience, and proactive decision-making. My name is Sebastian Mansell. I'm Senior Director of Product Management here at TigerGraph. I lead our Savannah Cloud product, which combines the power of graph technology with the scalability of cloud to solve some of the most complex data challenges enterprises face today. And I'm really excited to share this webinar with you today because, as you'll see, digital twins represent one of the broadest and most impactful applications for graph technology, spanning industries, use cases, and mission-critical operations. All right, so let's get started. What is a digital twin? So a digital twin is a real-time digital replica of a physical system. It can represent anything: a supply chain, a manufacturing line, an IT network, or even an entire transportation system. What makes digital twins powerful is their ability to stay continuously synchronized with live data. So this enables a dynamic cycle of observe, predict, and optimize. So with this feedback loop, you can simulate scenarios, forecast outcomes, and proactively fine-tune operations before problems arise. So think of it like a Google Maps with live traffic. It's not just a static map, but it is constantly updated to reflect everyday bottlenecks, reroutes as condition changes in real time. So why are graph databases uniquely suited for powering digital twins? Well, one is they are connected. So graph databases continuously ingest live data streams, keeping the digital twin always synchronized with the latest state of operations. They're also contextual. They naturally model complex multi-hop relationships, revealing hidden second and third tier dependencies that traditional systems often miss. And they're computational. TigerGraph in particular is really strong and enables in-graph analytics, allowing you to run advanced algorithms, simulations, and what-if scenarios directly on live connected data. Finally, they're actionable. With TigerGraph's sub-10 millisecond multi-hop query performance, you can generate real-time alerts, predict insights, and automate operational responses as conditions evolve. So let's take a closer look at how TigerGraph enables operational intelligence, helping organizations move from reactive to proactive, from fragmented to fully optimized operations. Enterprise often struggle across multiple stages: observing, controlling, analyzing, tracing issues, optimizing performance, and building resilience against disruptions. TigerGraph addresses these challenges through its scalability. It can process billions of edges with sub-second multi-hop traversal, delivering a complete real-time view across highly connected systems. It's also highly performant. It leverages compiled GSQL and parallel compute for efficient, high-performance graph analytics at scale. And then it comes with built-in 50 algorithms, and it is integrated with machine learning pipelines and native graph neural networks for advanced predictive analytics. And finally, it comes with visual tools like Graph Studio and Insights to make graph exploration intuitive, even for non-technical users. And we'll see later in the webinar a demo of those capabilities. And the results, you can model entire ecosystems with full relational context. And you can perform real root cause analysis and impact tracing 10 times faster. So let's take an example with a very recent example, the CrowdStrike global outage. So about a year ago, CrowdStrike released a faulty update that triggered a massive global IT disruption. The update propagated rapidly across systems worldwide, causing servers to crash and bringing down countless organizations. So a few key issues contributed to the scale of the failure. One, there was no system-wide simulation prior to the rollout. Second, CrowdStrike had no visibility into downstream dependencies, making it hard to assess the full scope of the impact. And then third, there was no scenario-based retesting to evaluate potential failures and failure propagation. And the result, over 8.5 million systems impacted, an estimated 5.4 billion in financial losses, and widespread disruptions across hospitals, banks, airlines, and critical infrastructure globally. And I remember this keenly because I was actually flying that day and my flight was delayed by 6 hours. And I considered myself lucky given the scope of the outage. So had a graph-powered digital twin been in place, CrowdStrike could have mapped all system dependencies up front, simulated the rollout to identify high-risk nodes, and proactively detected cascading failure paths before deployment. So this incident is a reminder of how interconnected systems amplify risk when dependencies are not fully understood. Another example is the Baltimore Bridge collapse, really showing how fragile interconnected systems can be. In March 2024, a container ship lost power and collided with the Francis Scott Key Bridge, causing the entire structure to collapse into the shipping channel. So the impact was swift. The Port of Baltimore was shut down for 11 weeks, one of the busiest ports on the East Coast. And economic losses were estimated at $15 million per day, with total financial impact exceeding $10 billion. With a graph-powered digital twin, port authorities and logistics providers could have modeled all transportation dependencies across truck routes, marine traffic, and port operations, simulated alternative rerouting scenarios to neighboring ports, quantified downstream financial impact in real time, accounting for added cost, transit delays, and capacity limits. So by simulating complex dependencies ahead of time, graph-powered digital twins provide decision makers with actionable options before disruptions turn into crisis. And then our last example is the Suez Canal blockage a little further back in 2021. But it really shows how fragile global supply chains can be. A massive container ship ran aground, blocking both directions of the canal for 6 days, essentially shutting down one of the world's most critical shipping arteries. Now, there were over 400 vessels stranded, waiting to pass. And there was an estimated $9.6 billion worth of goods that were delayed every single day. That's nearly $400 million per hour. And roughly 12% of global trade was impacted. Again, with a graph-powered digital twin, shippers and port authorities could have pre-identified choke points like the Suez Canal and modeled a full range of downstream dependencies, simulated rerouting alternatives through other ports or shipping routes, and quantified cascading delays and financial impacts to guide contingency plans in real time. All right, so now let's look at real life customer examples. So in this case, we're looking at an automobile manufacturer who's facing supply chain risks. So like many manufacturers, this company was dealing with increasingly complex supplier networks where certain parts were at risk of shortage, and they needed to quickly identify which alternate supplier could fulfill these parts. They also needed to understand which orders were exposed based on their supplier risks, and whether high-risk suppliers were being inadvertently prioritized for support. So TigerGraph helped by modeling the full network of parts, suppliers, orders, and dependencies. So not just direct connections, but multi-hop relationships across the entire supply chain. And with graph analytics, they were able to expose hidden supplier dependencies that weren't obvious in their traditional systems, quantify risks across both orders and suppliers, simulate alternate sourcing scenarios to evaluate different mitigation strategies. And the value delivered was significant. They resolved blind spots that had historically led to unexpected production delays. They were able to move to proactive sourcing strategies, anticipating disruptions before they occurred. And they optimized contract and order planning, ensuring that procurement decisions align with the actual risk exposure. So this is a perfect example of how graph-powered digital twins go beyond just mapping. They enable simulation, risk quantification, and informed decision-making across complex supply chains. So now let's look at another industry application. This time it's in IT infrastructure optimization. And this was for a global payment network. This was actually Visa, I believe. Now, in large IT environments, in large enterprises, these IT environments are extremely complex with many interconnected components. You have arrays, pools, logical units or LUNs, virtual machines, servers, and applications. So using graph analytics, they were able to build a real-time operational map of these dependencies, allowing them to ingest IoT sensor signals to monitor hardware health and identify at-risk components in real time. So if a component like a LUN, server, or application shows stress or failure risk, the system can assess the downstream impact across workloads and proactively reallocate resources. So this ensures that critical applications remain available even if the underlying infrastructure is degrading. And the real power comes from the ability to simulate cascading effects of potential failures. So allowing IT teams to predict where capacity bottlenecks can happen, preemptively offload workloads from failing components, and avoid service disruption by optimizing storage, compute, and network usage dynamically. So this is yet another example where graph-powered digital twin can transform static monitoring into proactive operational intelligence, keeping critical systems running smoothly, even in the face of complex multi-layer risks. So here's an example from the utility sector, specifically real-time management of electric grids. Electric utilities face an enormous challenge. They must detect overloads, rebalance power, and reduce outage risks, often in real time. And they need to do this without lengthy data prep or complex ETL pipelines. And this is where graph technology can be transformative. The Tiger Graph solution allowed this utility to model the entire grid as a graph, where components like substations, transformers, loads, and lines were all interconnected. And using this operational graph, utilities can compute power flows and generate estimations directly from raw operational data with no need for data aggregation or pre-processing. So Tiger Graph's massively parallel computing allows these complex calculations to be done at scale, balancing load spikes in real time. But the real power comes from simulation. Utilities can run continuously what-if scenarios to assess grid stability under different load conditions and simulate failure. This helps operators build stronger contingency response plans, knowing exactly which part of the grid are most vulnerable. And the results are meaningful. In this example, utilities were able to reduce outages by 25%, directly improving service reliability while reducing operational risk. So once again, a real-time graph-powered digital twin enabled a level of visibility, agility, and resiliency that traditional grid monitoring systems simply cannot deliver. All right, let's take a look at how a graph-powered digital twin can support predictive forecasting, particularly in complex supply chains. So this example comes from a large US technology manufacturer based in the Bay Area. So the process starts with data input. We pull in data from multiple systems. So think of ERP, CRM, IoT sensors, combining both batch and real-time streams to create a continuously updated data foundation. Then we apply graph modeling. So the graph models relationships across various entities, SKUs, warehouses, suppliers, carriers, and customers. And rather than analyzing isolated data points, we map how entities are interconnected. So we're exposing multi-tier dependencies that impact supply and demand. Next comes feature engineering. So graph algorithms like shortest path, page rank, and node similarity helps us uncover hidden relationships, supplier influence, and inventory risk patterns. These graph-derived features are often much more informative for forecasting models than raw tabular data and significantly improve forecasting accuracy. Then we move to AI models. So we train machine learning models such as XGBoost, as well as graph neural networks using frameworks like cuGraph and PyG. Now, GNN excel at learning from structured, interconnected data, where relationships between entities are critical for predictive power. And finally, we produce forecasting output. So predicting which SKUs are at risk of stockouts, identifying potential route delays, forecasting supplier instability based on their interconnected dependencies. So this end-to-end pipeline from raw data to relationship modeling to AI-powered forecasting enables companies to proactively plan for disruptions before they materialize. And the result, what once took 10 weeks to forecast can now be generated in just minutes, delivering faster, more resilient decision-making. All right, in this example, we're going to tie everything together. We're going to show how graph-powered digital twins enable rapid response during disruptions. So as we've seen so far in supply chain, disruptions are inevitable. We've mentioned the three catastrophic examples at the beginning of the webinar. Disruptions will happen. But what matters most is how quickly you can trace the downstream effects of a disruption, identify alternatives, and re-optimize the production plan. So here's the scenario. So one, a key rubber supplier becomes unavailable due to political unrest. So using graph analysis, we immediately run breadth first search and shortest path algorithms to trace how this shortage will affect downstream parts, so like tires, car rims, and final assemblies. And this provides an instant report on delays, cost, and affected orders. But we're not just reporting, we're also simulating recovery. So the system identifies alternative sources, in this case, supplier S11, and we can assess how quickly this alternative can fill the gap and automatically generate a revised production plan. So without graph-powered simulation, this kind of impact analysis could have easily taken days or weeks of manual analysis across disconnected spreadsheets and systems. But with digital twins and graph analytics, it happens in seconds, enabling proactive, data-driven decisions that can save millions of dollars in avoided downtime, missed orders, or customer churn. All right, in addition to responding to disruptions, graph-powered digital twins also help us diagnose and resolve root causes of production or delivery failures. So here's the scenario. A certain lot of car wheels sets have a known defect. Right. So using graph, we immediately trace upstream causes with a click, leveraging algorithms like breadth first search. The system identifies all the upstream suppliers, sites, and components that feed into the faulty wheel set, not just direct suppliers, but multi-tier relationships. Now imagine that there's a second concurrent problem. For example, an issue with truck wheel set. And the beauty of the graph is that you can analyze both problems simultaneously, identifying overlapping nodes and suppliers that might contribute to both defects. So this overlap highlighted in red here, helps zero in on likely root causes much faster. So in traditional systems, root cause analysis often requires manual sifting through siloed ERP, supplier, and manufacturing data. This can take weeks or months. With graph analytics, this multidimensional root cause analysis happens instantly, allowing you to reduce costly failures, customer returns, loss of trust, and brand reputation. So this level of speed and precision is only possible because the digital twin captures both the entities and their full set of relationships. So beyond reacting to disruptions or tracing root causes, graph-powered digital twins also allow us to build proactive resilience. So the goal here is to stay near optimal operations even when the unexpected disruptions occur. So to do that, we ask which nodes or links are most likely to be disrupted, and we analyze the aggregate probability of upstream success. Which shocks would cause the most costly disruption, and we calculate the aggregate downstream cost and delay exposure. And this helps us prioritize where the focus. This helps us prioritize where to focus mitigation strategies. So in this example, running the PageRank algorithm, there we go. We see that the controller node has the highest influence, meaning that many components depend on it. A failure here could have widespread downstream effects. And additionally, Site 8 is identified as a sole source for both the controller and a sensor, making it a vulnerability from a supply chain perspective. So with this insight, teams can diversify sourcing, build buffer inventory at most critical points, and proactively design redundancy into the system before any issues arise. And this is the ultimate value of a digital twin. Not only seeing what's happening today, but continuously simulating where you are most exposed tomorrow and designing resilience directly into operations. All right, so in addition to improving resilience and root cause analysis, graph-powered digital twins also enable us to optimize overall efficiency and throughput. So here we focus on two important aspects. One is shortest path analysis. So we can analyze whether there are more efficient routing paths between stages in the process. So for example, is there a way to move raw materials through the network faster, avoiding unnecessary intermediate stages and reducing cycle time? Second, maximum flow analysis. So this helps us evaluate the total output capacity of the system based on the carrying capacity of each component. The maximum flow algorithm calculates how much production can be sustained if every part of the network runs at full capacity. And this allows us to identify bottlenecks that constrain total output. And in the supply chain context, this helps companies balance resource allocation, evaluate investment trade-offs, and maximize throughput while maintaining quality and stability. So by simulating different load scenarios, we can directly measure cost versus benefit for process improvements before making operational changes. And once again, this capability is only possible because graph models the full structure of interdependencies, enabling both operational optimization and strategic decision-making. All right, so let's take a moment to summarize some of the core graph algorithms powering real-time digital twin use cases. So breadth first search is used to explore everything downstream or upstream from a node. For example, if a supplier fails or a part is delayed, breadth first search helps us trace all the impacted products, orders, or customers instantly. Then we have PageRank. The PageRank gives us a way to measure influence or importance. In a supply chain context, for instance, we can identify which nodes, such as a component or a supplier or a site, have the most downstream impact if they go down. And this is critical for resilience planning. Shortest path helps us find the most efficient route between 2 points. So it's useful for rerouting logistics, rebalancing production flows, or assessing recovery options during a disruption. Maximum flow looks at the total capacity through the system, and it helps us understand how much throughput we can achieve, where our bottlenecks are, and how to optimize system-wide efficiency. Node similarity compares nodes based on attributes or structure. This is especially valuable for finding alternate suppliers or parts that can serve as backups when primary sources become unavailable. So all of these algorithms run in graph in real time, enabling digital twin that's not only accurate and contextual, but also responsive and intelligent. All right, so this is the slide where we tie it all together with the various customer successes that TigerGraph has delivered. So we've shown crisis, operational use cases, and deep dives. But now let's quantify why this matters. So forecasting. So what used to take 10 weeks is now completed in minutes with nearly 20% better accuracy. That's fewer stockouts and less capital tied up in inventory. Parts and supplier risk. I think this was the Jaguar Land Rover use case. By running automated what-if simulations in TigerGraph, they were able to slash emergency air freight by 30%. And Visa reduced mean time to resolution from 45 to 15 minutes because engineers were able to see the blast radius instantly of their network and IT operations. And energy utilities, the power flow calculations that took an hour now finish in under a second, cutting outages by 25%. And then finally, engineering change orders, thanks to a multi-hop BOM twin, there's companies were able to push design changes through 20% faster. So across the board, TigerGraph delivers speed, insight, resilience, and productivity. So the 4 pillars of an effective digital twin program. All right, we're now going to see a demo of TigerGraph. Hello, everyone. In this demo, I will walk through the Network Infrastructure Solution Kit in TigerGraph Savannah. Savannah includes 9 solution kits, each providing pre-built schemas, queries, and sample data. These kits help users explore graph capabilities or accelerate implementations for use cases such as fraud detection, entity resolution, product recommendations, and in this case, network infrastructure. To deploy the kit, I navigate to my Savannah instance and select Install Solution. So here I see the list of the 9 available kits, each with a description of the use case and helpful tags to make it easy to find the right one. So I'm going to go ahead and select the network infrastructure. I can see the schema that's provided with the solution kit, as well as the fact that it's already deployed on an existing workspace. I will give the graph a name and select the workspace to deploy it to. And here I have the option to either deploy the kit with the sample data set provided, I can deploy it with my own data, or I can deploy it with no data. And then finally, I can see all of the vertices and the edges that are provided in the kit. As a reminder, a vertex is the equivalent of a database record, and an edge defines the relationship between these records. So I'm going to go ahead and navigate to my workspace, and we'll go to Graph Studio. In Graph Studio, I will select my workspace. And here I can design schema. I can load data or explore graph. So I'm going to start with the design schema page. And as you can see in this page, I can see all of the vertices and edges that are part of the schema. And I can see that the schema is centered around the event vertex. That event vertex is connected to time dimensions, including time, date, month, and year. It's also connected to incident and alert vertex, as well as a device vertex. And I can see all of the relationships defined by the edges as these lines between those nodes. Now, devices has 4 different types: server, switch, firewall, and router. And I can see that these devices can be connected to each other as defined by this edge here. In this page, I can create a new vertex simply by clicking on the plus button. I can provide it a name. Let's say if I wanted to have a new device type, and I can modify attributes or build new relationships. So moving on to load data. So here I can see my graph statistics. In this demo, we have approximately 3,200 vertices, over 6,000 edges. It also defines the statistics per vertex type. So I can see that I have 120 servers defined and 954 events. Under Explore Graph, I can look at the specific data set. So I'll pick the device vertex, and here I can see the data. And if I click on each of these dots, I will see the attributes for the data. So moving on to TigerGraph Insights. So TigerGraph Insights includes 4 dashboards that are purpose-built for this solution kit. So we'll start with the Topology Exploration widget, which allows you to visualize how devices are connected. So on the left-hand side, I start with my router 1 device, and I can see that it's connected to 2 firewalls, multiple switches, and servers. So I can see all of the connected devices for that router. On the right-hand side, I have a similar view, but starting with firewall 3, and I can see the switches and servers that firewall 3 is connected to. If I move down, I can see my entire network. So very clearly here, all of the device connections are shown. And I can also see that that my network is essentially composed of 3 different subgraphs. So moving on to the failure impact radius. Now this view or this page highlights single points of failure. So again, if a device fails, I want to be able to identify other devices that could be affected. And a device is considered failed if it no longer has a path back to an active router. So for example, here on the left-hand side, I can see that my firewall 7 is connected to switches 18 and 20. And if firewall 7 fails, then those switches will fail as well as all of the servers that are connected to them. I could see the same data here, but within the subgraph. So I have my firewall 7 and all of the connected devices in red. So again, if firewall 7 fails, all of these red devices will fail, and I can see that as part of my subgraph. Moving on to the event visualization. Here I can see all the lists of events and alerts. And I can see, for instance, that this device, switch 6, was impacted 7 times during the time frame that I'm looking at. And I could see that, again, the incident here impacted this firewall and this switch. And then finally, I have the causality tracing. So here I can look at, I can trace the sequence of related events and incidents. and we can see the incidents that are related to a specific alert. So starting on the right-hand side, I can see that my server internet connection loss alert is connected to this incident, affected server 36, and I can trace it all the way back to a switch failure. And I have a similar view here on the right-hand side. I can see that, again, my internet connection loss alert affected server 36 and server 54. Now, finally, I'm going to go and explore my GSQL editor so I can look at the queries. So I'll go to Query Editor. And here under the Query tab, I can see a folder with all the queries that are included with the solution kit. And I can click on each of these and I can edit the queries or I can just simply run them. All right, and this concludes our demo today. Thank you for watching. I hope this provided a helpful overview of how the network infrastructure solution kit can improve visibility and support faster incident resolution. Okay, so let's go back to presentation. All right, excellent. So let's close by highlighting why TigerGraph in particular is well suited for powering real-time digital twins. So one, TigerGraph is connected. TigerGraph supports real-time ingestion from both streaming and batch data sources. Now, this ensures that your digital twin remains fully synchronized with the live state of your ERP systems, IoT devices, event feeds, and transactional systems. Nodes and edges are automatically updated to reflect new routes, new parts, or emerging failures in near real time. TigerGraph is also contextual. Graph allows you to traverse 10 plus hops to reveal second, third, or even fourth tier dependencies that are often invisible in relational systems. And then algorithms like breadth first search, shortest path, and PageRank help expose hidden risks and cascading impact across complex supply chains and operational networks. And then TigerGraph also has built-in scenario simulations. So you can run in-graph simulations directly using built-in algorithms and GSQL queries for true what-if analysis. Our native GNN integration also enables predictive forecasting using your live operational graph as training and context. And then finally, TigerGraph scales and performs. TigerGraph is built for distributed storage and parallel compute, handling billions of nodes and edges. Despite this scale, we deliver sub-second query performance, enabling real-time operational decision support. And so this is why TigerGraph stands apart in enabling operational intelligence, combining speed, scale, depth, and actionable insight into one integrated platform.